look at electronegativity and polarity. All right, we looked at electronegativity a few chapters ago. We talked about the different trends for the periodic table. So we know a little bit about what that is. We're going to recap, and then we're going to deal with how that ties into something being polar or nonpolar. Okay, so first off, a chemical bond's character is related to each atom's attraction for the electrons in the bond. So we're all about our electrons and how attracted they are to one atom or another atom. Okay, and the big idea here is that if you think about it with people, okay, the stronger you are, the more easily you can do pull-ups. So just as people have different abilities for doing pull-ups, atoms have different abilities to attract or pull in electrons. You have to think of it as a tug of war between two atoms on the electrons. And we're going to kind of refer back to this picture here a little bit later. But you're really looking at the two nuclei. Okay, so this would be like my bond here that they're sharing the electrons. And one might pull a little bit better than another atom. Okay. First off, we're going to kind of just do a little definition. And that's what's called electron affinity. We don't do a lot with this other than I really just tell you kind of what it is. Okay, electron affinity is the affinity that something has for an electron, and by affinity I mean how much they kind of like them. All right. This is really just the tendency of an atom to accept an electron. So what we're dealing with here is the opposite of ionization energy. So we're actually dealing with taking an electron. Okay, it's kind of like a parentheses instead of an I there. Okay, so we're dealing with the opposite of losing an electron or removing an electron to somebody. Somebody is actually now accepting the electron. All right, which is going to be a little bit different than electronegativity. Okay, and that's the more important one here. Electronegativity is just the ability to attract an electron. So you're not actually accepting one from somebody else or receiving it. You're just kind of attracted to it a little bit more. So again, we're looking at the ability of an atom to attract an electron in a bond. Okay, if they are more electronegative, that means they have more pull. And I always do electronegative as En. All right, if we want to remember, I'm also going to squeeze in here, okay, that fluorine is the most electronegative. So that means that it has the most pull on its electrons, right? And every element has a set number. So every element actually has a set value that's associated with it. Okay, we don't really deal with the numbers quite as much. We're going to look at it here in a second, but you really just got to know that fluorine is the most. Everything close to fluorine is a little bit less, and then the further you get from it, the lower the number gets. All right, but everything does have an actual set number to it. The highest one is actually a value of 4. All right, so there are types of covalent bonds that are based on the electronegativity differences. So there are kind of two types of covalent bonds, all right, based on how much something wants to attract an electron in that bond. The first one we call a pure covalent. Sometimes they're also called nonpolar, but usually if it's just a bond, we call them pure covalent. Over here in the chart, they call them nonpolar, but I usually call them pure. Okay, that means your electronegativity difference is really just 0. All right, I know the chart over here says it's from 0 to 0.4. 0.4 is really not going to be much. We tend to stick with really just pure ones being just 0. Okay, so what that means is these are the same element, okay, that are bonded. So the same element is bonded, all right, which means that you have equal strength, and by strength I mean pull on your electrons. So it is an equal sharing of electrons. When we talk about electronegativity, I tend to think of it in terms of strength. The stronger elements want to pull electrons to them. Okay, so it'd be something like fluorine. So I tend to think of fluorine as being stronger, having the most pull, okay, versus something like hydrogen that has very little pull. Okay, the other type of covalent bond is a polar covalent. Okay, a polar covalent is anything with electronegativity difference between 0.4 and 2. Anything over 2 is really an ionic bond. Okay, but between 0.4 and 2, we're dealing with an unequal sharing. And again, we're sharing electrons, which means then that we have an unequal pull on those electrons. Okay, so you're either going to have a pure covalent or a nonpolar, or you're going to have a polar covalent. Anything over a value of 2 is going to be an ionic bond, because that means we're not even sharing anymore. Okay, we're actually, one's gaining and one's losing, so we're going to write that in there. So you either have a pure covalent, a polar covalent, or what we looked at before, an actual ionic bond. All right, where again the pole is so different that they're actually not sharing electrons anymore. One atom lost the electrons and one atom gained the other electrons. Okay, we're going to look most at the polar covalents because those are the most interesting and those are the newest ones. Okay, a polar covalent bond again is a tug of war between two atoms of unequal strength. And what that means is that your electrons are going to be pulled more towards one of your atoms, and that's going to be the more electronegative one. Which then means that it's going to spend more time around that atom, or the electrons are going to spend more time. So we'll look at this picture as an example, okay? This right here would be a non-polar covalent bond because notice how it's right in the middle there, sharing very equally. If this would be at one side or more towards one side than the other, so this pair of electrons right here, these are my two nuclei, my electrons may either sit closer to one or the other, okay? That would be a polar covalent bond because now whatever atom this one is could pull these electrons closer to him, makes him more electronegative, which would make that bond polar. The word polar comes from having a pole, a positive end and a negative end, okay? So what happens is it makes this end down here, okay, since you're pulling those negatives closer to it, it makes this end right here a little bit negative. And it makes this end right here of this atom a little bit positive. But it's not a full positive and a full negative because it's not an ion. So what they are, they're called partial charges. So we have this weird little symbol, okay, that kind of means partial. It's actually a Greek letter, okay? So we'll see it down here. I'll draw it again. All right, but again, it causes a partial positive and negative side or end. And you'll see the little symbol, it's like a little, it's actually a delta. Okay, it looks kind of like a little S. You have a positive end and a partial negative end. Because again, they're just they're pulled one way. You're not taking them, they're just pulled that way, so this side's a little more negative, that side's a little more positive. That's all that's dealing with, okay? So if we look at this picture down here, okay, we have hydrogen and chlorine bonded together, all right? The electronegativity value of chlorine is larger than hydrogen because chlorine is closer to fluorine, okay? So I have a difference here. If I knew the numbers of 0.96, all right, all I have to do is subtract them if they gave you numbers. Usually I don't, okay? You usually look at, oh, okay, those are two different things. One's going to pull more. Well, which one's going to pull more? The one that's closer to fluorine, okay? So chlorine's going to be the one, all right, that is more electronegative. Why? Again, because he's closer to fluorine, which means his side is going to be a little bit negative. And the hydrogen side is going to be a little bit positive because just like above, okay, if I have an HCl bond, those two negatives that are in there, so I have two little electrons, okay, they're going to kind of move themselves and they're not going to be right in the middle. They're going to be a little bit closer to chlorine than they are to hydrogen. Still bonded together, but just a little more skewed to that particular side, okay, which again makes this side a little negative, makes this side a little positive, okay. And the only thing you really want to add, all right, is that the further they are apart, so on the periodic table, which means the bigger your electronegativity difference is, it's going to be a more polar bond. So the further apart on the table they get, the more polar that particular bond is going to be. So since H and Cl are pretty far apart on the table, that's a pretty polar bond. If you would have a bond between something like S and O, so I bonded S and O together, those are a little bit closer together on the table, this particular bond is not going to be as polar as the HCl one. These electrons are going to sit a little more in the middle than they would on another one, okay, one that was further apart. One more way you'll see this denoted, okay, with a positive negative end is you'll see a little arrow, okay. You'll see actually something like this with a little positive end on it. That's the positive end on the left. This is the negative end. What that means, it's just another way to write instead of the little delta symbols or little S symbols there. Okay, what that means is that your electrons will kind of travel that way. So it's just kind of another way to write which side's positive and which side's negative without saying, oh, okay, this is an ion that's positive, this is an ion that's negative. Again, remember, they're still shared, they're just not shared equally. Okay, this whole front page is all dealing with the bonds. Okay, if you flip it over, or flip your notes over, okay, now we're going to look at our actual molecules. So if we do polarity and molecular shape, we're now going to look at the molecules. Okay, so no longer just the bonds, but the actual molecules. Okay, so bonds can be either polar or nonpolar, and since bonds make up your molecule, that can make my molecule either polar or nonpolar. Okay, so bonds can be polar or nonpolar. Since bonds make up a molecule, molecules can be polar or nonpolar. And really what we care about more is the molecule part. Which part of my molecule, is this molecule polar or is this molecule nonpolar? Okay, we're going to take, for example, letter B there in the picture. Okay, so if we look at B, all right, we read the little caption. It says that the symmetry of CCl4 molecule results in an equal distribution of charge and your molecule is nonpolar. So what that's talking about, okay, is that you're going to have an equal distribution of charge. So even though that carbon-chlorine bond is polar, all of those bonds are equally pulling outward. How do I know they're pulling outward? I know they're pulling outward because chlorine is more electronegative than carbon. So all of my electrons are going to want to go that direction, out towards the chlorine. So all my electrons are going that way. Well, if everything is pulling out towards my chlorine, okay, everybody's pulling, all right, all the angles are the same from that lovely symmetry of the tetrahedral we looked at last chapter. Everything's pulling the same. Since everything's pulling the same, it all cancels. It's like if you have a tug of war. So if you disregard all the little molecules and such, and think of it as a tug of war, my center thing here, okay, if I have four things, okay, 4 pieces of string that are all attached to that center, and there's a person on each end of the string, and everybody pulls the same, we're all going to cancel. You're not going to go anywhere. Since it's all going to cancel, it's nonpolar. So this is a nonpolar molecule. There's a difference between the molecule being nonpolar and the bonds being nonpolar. Here we're talking about that my molecule is nonpolar. Okay, now what if they don't all cancel out equally, which actually happens more often than not? Okay, we're dealing with ones like A and C. Okay, when we deal with A and C, now we're talking about, okay, something's not going to cancel quite right and we're going to end up being polar. Because if we read the little captions for A and C, the last little sentence there talks about that the molecule is polar. So I'm going to look at what makes those ones polar. All right, so I'm just going to backtrack for a second there and talk about lone pairs, because actually both of the molecules in A and C have lone pairs. Okay, you can't see the ones over here because they didn't draw them in, but water has 2 lone pairs. Okay, and then deal with lone pairs. Okay, you got to think about what lone pairs are. Lone pairs are electrons. Okay, so since they're electrons, all right, that makes a very negative end to wherever they are located on the molecule. So it makes that end of the molecule negative. And really negative, because that's a whole charge of that electron. Okay? So they will usually make a molecule polar. The only way you can have a lone pair and not be polar is if you had 2 lone pairs. But, okay, so the only way to cancel out the pull of your lone pair is to have a second lone pair 180 degrees away. So all the way on the top, all the way on the bottom, now they'll cancel. That only happens for one particular shape. Okay, and then that's it. There's only one of those. Usually, if you see a lone pair, that molecule is polar. So if we look at A and C both have lone pairs. Since they both have lone pairs, okay, they're both polar. I will also add, though, another way you can be polar is if you would have different elements around the center. And why that makes a difference is because if you have a different element around the center, it's going to pull differently. If they pull differently, that makes it polar because it's going to make that side positive or that side negative. So if we would change, say, letter C here, and I would change that to, instead of being an H here, we're going to make this I don't know, a fluorine. All right? That's totally going to make everything different because this is going to pull differently than the other H's are going to pull. So since it's going to pull differently, now you're thinking by tug of war. Now I have my center. I have one pulling this way. I've got another pulling that way. I've got another one pulling this way. And I got my lone pair pulling some other way. Those are not going to equal out. Even if you had two lone pairs and two of the same atoms, like this one, that does not cancel. These lone pairs do not cancel because they are not 180 degrees apart. They're at some other angle. Okay, we talked about those last chapter. All right, but they're not 180 degrees. Even if you had, for example, this is what always gets people, if you had carbon in the middle, and I had a fluorine, a fluorine, a chlorine, and a chlorine, okay? They're different, but you say, oh, okay, well, he's going to pull this way, they're going to pull this way, they're going to pull, they're going to pull. Well, I have two of the same opposites, so they're going to cancel. That's not how that works, because you have to remember that this angle right here is not 90, okay? Remember that angle, not 90 degrees. Since it is not 90 degrees, it does not cancel, okay? You have to have every single element around there being the exact same to cancel those poles out to be nonpolar, which is why I mentioned earlier that it's way more likely to be polar than it is to be nonpolar. Okay, so let's try a couple of examples, all right? Because to draw the Lewis structure and determine whether each molecule is polar or nonpolar. So what I want you to do is go through for all those 5 and draw the Lewis structures for all of them. And then we'll go through and decide whether that makes that polar or nonpolar. Okay, so there are my 4 Lewis structures. I left off my lone pairs just for the sake of ease of seeing these. Okay, so if we look at our first one, SF4, okay, this one would be polar. Okay, I'm going to put P or N. Polar because that lone pair is going to make that side more negative than the rest of them. Polar. For the second one, that one's going to be nonpolar. Okay, because all those F's are the same thing. They pull all the same. They pull equally. They cancel out. Nonpolar. SCl2 is going to be polar. Because like I just said a minute ago, these 2 lone pairs, even though there are 2 of them, and they usually are drawn like that, they're not 180 degrees apart. They do not cancel, which makes that molecule have a negative end by the electrons and a positive end somewhere else. This one, the next one on the other hand, though, should be nonpolar because they're going to pull equally. Each of those S's is going to pull outward, okay, pull those electrons outward, and they cancel. CF4 is also going to be nonpolar, okay, because all of those F's are going to pull equally. Now, like I mentioned a minute ago, if you change one of these fluorines to something else, that makes it polar. Because now that particular atom or element is not pulling on those electrons the same as everybody else, which throws everything off, which makes it polar.